Welcome to this tutorial about coupling in proton NMR. Coupling tells you how many hydrogen atoms there are on neighbouring carbon atoms, and therefore it's very useful for determining the carbon skeleton within your molecule. This is the spectrum without coupling. The red hydrogen is at a slightly lower chemical shift than the green one. I've just put in some markers here to indicate the original shift of these protons. Now we can imagine that the red proton, Hb, can be spin up and therefore aligned with an external magnetic field. And as a result of this, Ha will experience slightly more magnetic influence than it did before, because it experiences both the external magnetic field and the magnetic field of the nearby proton. And so its peak will be shifted to a slightly higher value. Alternatively, Hb could be aligned against the applied magnetic field. It could be spin down, and therefore from the perspective of Ha, it will experience slightly less magnetic influence than before, and so its peak will be moved to a slightly lower chemical shift. So the presence of Hb causes Ha to be split into two, and that's called a doublet. Now this effect will occur in reverse, i.e. the shift of Hb will move up and down slightly depending upon the spin state of the nearby Ha, and so Hb is also split into a doublet, and when we've got these this effect occurring, where we've got these two doublets, that is called coupling. So I've just put on the final spectrum and get rid of the red and green lines, and the pair of doublets here showed that these protons are close to each other within the structure of the molecule, and as you can see they're on the same benzene ring and close to each other in the molecule. Continuing with coupling in proton NMR, here is the low resolution spectrum for this molecule, so before coupling. The two red hydrogens give this peak, and the green hydrogen gives this other peak. I'm going to put markers on for the original shifts, and then imagine that one of the red hydrogens is spin up, which will cause one of the green hydrogens will be affected by this and move to a slightly higher chemical shift. In fact, there are actually two red hydrogens, so they could both be spin up, and this would mean that the green experiences more magnetic influence and is moved slightly higher upfield. Alternatively, both of those red hydrogens could be down, and so that would mean that the green hydrogen would feel less magnetic influence, and so we'd see a peak shifted to a lower chemical shift. There are two combinations of being one spin up, one spin down, and so therefore we'd get a superimposed peak on the original chemical shift. And the same thing can occur in reverse. The green hydrogen could be spin up, which will cause the red peak to move up slightly, or it could be spin down, which will cause that red peak to move down slightly. So starting from the original uncoupled spectrum, after coupling, we see the red's been split into a doublet by the one neighbouring green hydrogen, and the green peak's been split into a triplet by the two neighbouring hydrogen atoms. And this gives rise to, if you like, the n+1 rule. So that's stating that the number of lines a peak is split into is the number of hydrogens on neighbouring carbon atoms plus 1. So for the green hydrogen, there are two hydrogen atoms on the neighbouring carbon, and therefore the green peak is split into 3, into a triplet. And for the red hydrogens, there was only one hydrogen on the neighbouring carbon, the green one, and so this red line is split into a doublet. The effect can continue so that you can have quartets with 3 hydrogens on neighbouring carbons, or quintets, or even more. Next, I'll go through some examples of NMR spectra.